In this video, we are going to be talking about the importance of scan direction when analyzing eddy current data from an inside bobbin coil probe when testing tubing. But before we talk about the bobbin coil, let's talk about this Z-Tech pencil probe. This pencil probe has a pancake coil in the tip of it, and this is used for scanning the surface of conductive materials. Very thin because you can only inspect as thick as your coil is wide, basically, right? You're very much limited to the depth of this pencil probe. You're usually running at a high frequency also, but you can be basically scanning the surface and very near surface for discontinuities. But with a pancake coil, as long as you're scanning properly with 100% coverage and you're hitting potential flaws from different angles of attack with your coil, you can find indications, or you can find discontinuities in any orientation: circumferential, axial, volumetric. That's nice about pancake coils, as long as you have complete coverage. Now, next I'm going to hold up, this is another type of surface probe, but this has a self-comparison differential in it. So this is very typical of what you'll find in probes for weld scanning. Now, these type of probes usually have a line on one side of the coil, and you're going to want to be scanning in the direction of that line, either towards or away from. So the orientation of your probe is very important for your angle of attack when finding flaws. So you always have to know what coil orientation you have in your probe head. Now, when it comes to bobbin probes, I'm going to hold one up in front of the camera here. This is the Star bobbin coil probe. I don't know if you can see it there, but there's two coil windings there, and they're wound circumferentially around the probe body. So you can't really control the direction of your scan with the bobbin probe because you're either inserting it or retracting it. Now, in this orientation, this would be a vertically mounted heat exchanger, or if it was laying on the side, you would come in from the side. Actually, you'd still be coming in from the end, but it would be horizontal instead of vertical. So you can't really control your scanning direction. It's either in or out. But what you can control is whether you're recording data on the insertion or the retraction. Now, ASME code has you're required to record data on the retraction or on the pull, and the reason for that is because it gives you a more consistent scan. So what I'm going to do is start the tester, and I want you to pay attention to the strip charts over here. Now, the strip charts are an indicator of time, which can be used to estimate distance, and also it's useful for determining the location of flaws with respect to either tube ends or support structures like tube support plates. Now, when I start the tester in the recording mode, you're going to see that this data starts to play in from the top as it's recorded. And when you get to the bottom of the strip chart and I hit stop, you're going to have some data displayed. The thing that the probe saw first when I started recording is going to be at the bottom of the strip chart, so that's earliest in time data. And the thing up towards the top of the strip chart is going to be the last thing that the probe saw before I turned off the tester or turned off the recording mode. So that'll be your latest in time data. So I'm just starting the tester here, and you can see that strip chart moving. I'm going to insert the probe all the way out the other end. And what I'm going to do is clear the screen, and I'm going to let those strip charts play out. And I'm just going to do one consistent pull through the tube. Probe sees that first. Probe sees that last. Now I'm going to stop the tester. And what I'm going to do, that's the data up here. Let's see here, where is it? Right here. So the earliest in time data is down here. So this is useful when you have a calibration standard drawing. You can look at it, and then you can hold up your calibration standard. And if you can locate where the 100% hole is based on your drawing, then you can figure out what all the other flaws are. Now, the reason it's important that you understand the earliest in time data and the latest in time data is because when you analyze data, when you scroll through the data, you have to do it in the direction that it was acquired. So you don't usually start from the top of the data and scroll down. That would be doing it backwards. So what you want to do is start below the flaw, and then you'll just scroll up into that flaw, and if it starts down and to the right first, that's going to be in the flaw plane for differential signals, as long as it's between 0 and 180 degrees. And that's only if you calibrate correctly using the right frequencies for the material you're testing and wall thickness. So this is 100% hole, and I've already calibrated this particular indication. So the 100% through all hole starts down and to the right and goes up to null, and then the second coil will go in the opposite polarity and come back to null as the pair of coils goes past that 100% flaw. Now, if I were to get that whole flaw in the window, I have to make my window a little bit bigger here. Let's see here, display, data cursor. Miss 27, I gotta use a button because I don't have a mouse on it here. But if I measure this, it's 44 degrees. Ideally, it's supposed to be set to 40 degrees, but that's in the flaw plane, and that's where we set our 100% through all hole to basically 40 degrees. Now, when I'm scanning in the proper direction, moving up the strip chart, the next indication is from an 80% flat bottom hole. Now it's going to be about, what, 80 degrees? That about right? 77 degrees, so that's also in the flaw plane. Anything from 0 degrees to 180 degrees is typically in the flaw plane. Now, watch what happens if we scroll the data in the wrong direction. I'm going to go from the top to the bottom. And now as I scroll through that indication, I got to do a little bit slower. It starts up and to the left first, and then it goes down and back to null. If you were properly calibrated and you were scrolling from bottom to top and you saw this signal go up first and then down, you would disregard it as being non-relevant, or at least not flaw-like. So when determining if something is flaw-like, you have to be scanning in the proper direction. So these are just a few of the fundamentals that you need to know when you're analyzing tubing bobbin data. Thanks for watching.